Hello and welcome to a short podcast on the topic of superposition, part of wave characteristics, which is part of the waves unit for the IBDP physics course. So superposition gets mentioned here, and sketching and interpreting the superposition of pulses and waves. So that's what we're going to do. The basic idea of superposition is well represented by this photograph on the right here. Here you see obviously a pool or a pond of water, and raindrops are falling in it, and each raindrop as it falls imparts some energy and creates a brief disturbance, creating a series of circular waves which spread out. And as they spread out, as you can see from the photograph and from your own experience, they kind of pass through each other. They don't bounce off each other, they don't bend round each other. Each wave sort of independently passes through the other waves. But what does that actually look like when they meet? Well, when they meet, the surface of the water is represented by the displacement of the water is the displacement of the two waves added together. What do I mean by that? Well, and this works, by the way, I should say, for any waves. One of the essential ideas of this unit is that the mathematics and descriptions of waves are pre-universal. So any description we do for water waves can be probably applied to every other kind of wave as well. So electromagnetic waves, waves on the spring. Superposition is one of the fundamental properties of wave behavior, wave characteristics. So the technical way this is put is that if there are multiple waves present, then the displacement of any point is the vector sum of the contributions from the individual waves. So to find the displacement of the medium, the water, the electromagnetic field, whatever, at one point in space, you had to add all of the sums of what the individual waves are doing. And it's got to be the vector sum. Okay, so if they're both acting in the same direction, they will add. But if they're acting in opposite directions, then they will cancel to a certain degree. I summarize this as two statements. Waves pass through each other. They don't reflect, they don't bounce off, they don't bend round. Waves just pass through each other, and the displacements at any of the points add together. Now, courtesy of a couple of websites, we can do some good illustrations of this. So this is from New York University Tycho Slater's website. Got a couple of animations here. In each of these cases, we have two blue wave pulses. So it's just one pulse of a wave traveling left to right or right to left. And then the red line underneath represents the two of them added together. So here we have two waves, both of which are in the same direction. You notice they come together and they form a big wave as they pass and they move back again. Here, one wave is going up and the other wave is of the same magnitude, the same amplitude, so to speak, but it is now pointing down, and they kind of do that weird thing where they kind of merge and then they cancel each other out. So let's see if we can just show you that. They merge. Well, I just about missed it here, but they kind of cancel each other out and they pass by. And here we have one wave going up, one wave going down, but now they're not exactly mirror images. They look a bit different, and as they pass, they do that kind of weird shape. But at every point, we can freeze time if we want, whenever we want, at any point, the red line represents the two blue lines added together. And that's what the resultant wave will look like when we add them together. That's for wave pulses. So for, oh, I see, didn't know it did that, but anyway, that's for wave pulses. Just to get a little bit ahead of ourselves, one of the properties of waves is interference, and superposition is basically the principle behind interference. When two waves add together and they make a bigger wave as a result, we call that constructive interference. When two waves add together, but because one of them is relative to the other negative and they kind of cancel out, we call that destructive interference. So terms we'll be looking at in the future: constructive interference and destructive interference. That's wave pulses. With traveling waves, we can see something similar here. So these are animations. So on the left-hand side, we have S1 and S2 of the two waves. They are the same amplitude, they're the same frequency and wavelength, but they are, so to speak, traveling in opposite directions, and they will form the wave that you will see below. This actually is a special kind of wave that we're going to be looking at later, called a standing wave. The one on the middle is similar, except that the two waves are no longer the same amplitude exactly. So on the one on the left, they will go to a flat line at the point. The ones on the middle here will never actually go to a flat line, because they will never cancel out completely everywhere along the wave. And on the right hand side here, you've got two waves of the same amplitude but different wavelengths. You can see how they form a more complicated shape. Now, it's not exactly on the syllabus, but a useful thing to know is that if you're ever given a situation where you have one of these sort of complicated waves and you suspect it's made from one or more of these waves adding together, there is a way of doing an analysis to try and find out what those waves might be. And this is known as a Fourier analysis, and one of the algorithms that can do this kind of analysis is called a fast Fourier transform. It's a common feature in many software packages, many data analysis software, so it's one that you might be able to do. So you might, as a result of an experiment, get out something like this wave, or this function, this mathematical function, but it's a wave at the top here. And you might say, hold on, I want to know if it looks like it's made out of different cosine or sine wave functions. In fact, any function can be expressed as the sum of wave functions. And if you do the analysis, then you get a result something along the bottom here that says, yep, it's made up of a 50 Hertz wave, a 40 Hertz wave, a 30 Hertz wave, a 20 Hertz wave, and a 10 Hertz wave of different amplitudes, with the 50 Hertz one being dominant, which is a useful thing to be able to do. But it's not really on the syllabus, but you might find it useful for your practicals. One question about superposition from the Time Zone 1 May 2013 Standard Level Paper 2. It's basically a definition question, although for reasons unknown they don't use the word define. They say state what is meant by the principle of superposition of waves. So it's useful to know what the IB means by this. And so from the mark scheme, when two similar waves meet, the brackets there mean that that's not actually essential. The essential part is the resultant displacement is the brackets vector, so you don't need to write vector, but it is the vector sum of the individual displacements. So this idea that displacement and displacements, one word that is not there and that you must not use when talking about superposition is amplitude. Okay, the amplitude is the maximum displacement, but we're interested in all of the displacements through time and space. So don't mention amplitude, instead make sure you're talking about displacement when you're giving a definition of superposition. Okay, so we've talked about superposition, and we have sketched and interpreted superposition of both pulses and waves. Thank you very much.